Hello everyone, this is our product, the Dia-Cornea for the Diatech 2025. We are two students from AIMS New Delhi. My name is Janvi Banotra and this is Dhruv Advani. Now to speak about our problem statement, as we'd already spoken about it in the previous video, we are primarily focusing on developing a screening tool which is sensitive, which has early detection and is inexpensive. So there are current strategies in place which fulfill some of these criteria, but not all of them. So this is a review of the current strategies that we did. There is the Michigan Neuropathy Screening Instrument, which is a questionnaire. It has a poor diagnostic accuracy of only 7.4% without the clinical examination. Then you have the 128 Hertz tuning fork test, which is not effective in the early stages. Then there's the nerve conduction studies. It's time consuming. It requires specialists. Skin biopsy is present, but it is invasive. You need around a 2 to 3 millimeter big patch of skin. There's the pseudo scan. It has not been universally validated, and because it requires autonomic functions, it shows variation in time in temperature and humidity. And then there's the corneal confocal microscope, which is a very accurate screening tool. However, it is extremely expensive. So this is what we focused on. We modified this product to create the Dia-Cornea, which is a cost-effective, accurate screening and imaging device for early detection of small fiber neuropathy. So the impact, so we've already spoken about the background as well in the previous video. So now to talk about the impact that we think this tool can have. Obviously, it will allow an earlier detection before the onset of symptoms. It's cost effective, and with its AI integration with simple design will allow it to be used in low resource and minimal training. So now how it can affect the population of India is that the massive number of diabetic patients that we have can be screened and can be the progression of neuropathy can be checked. It will prevent the further progression to DFT, and it allows detection around 3 to 5 years early. Different surveys show that a minimum of 30,000 rupees is the expenditure once neuropathy sets in. It will reduce the burden on public health system, and it will allow quicker diagnosis with the help of AI integration. So these are our stakeholders and our buy-in. We've already spoken about them, primarily the diabetic patients, healthcare workers, government, and the investors. Then we modified and added some more stakeholders, the medical colleges, research institutions, insurance providers, and medical device distributors can also have different buy-ins for this technology.
Coming to the technical feasibility, so this is a gross overview of our product design, where we've planned to use an objective lens that's an aspheric singlet or achromatic doublet lens, which will replace the current oil immersion objective that is used, which is a lot more expensive. The light source that we have planned to incorporate into this device is a 650 nanometer laser diode. Our scanner, we have planned to use a galvanometer mirror in place of the resonance scanners that are traditionally used. In our detection system, we have envisioned CMOS cameras. These are not only a cheaper alternative to the currently used EMCCD cameras, they're also a lot more effective in identifying the nerve fibers. Then for the mechanical frames, we are going to replace the metallic frames with aluminum ones, and we're going to put in a physical pinhole, which is a 50 micrometer stainless steel pinhole that will eliminate the requirement of physical deblurring of images and make the images a lot sharper. The diagram that has been put in shows a schematic representation of how our corneal confocal microscope or the Dia-Cornea will work. Now coming to the AI integration part of it, we have envisioned the use of AI software for several applications. Firstly, we are planning to use the unit-based automated nerve segmentation to differentiate nerve fibers from the background. This is a software that will help identify pixels and the contrast between different pixels. Then we will use a machine learning classifier to grade the neuropathy that the patient is suffering from on the basis of branch length and density as well as the tortuosity of nerves. In all of this, we plan to keep a simple interface that is very easy to use by all healthcare workers. Now, validation of the data will be done in the same way that we described earlier using the AIMS dataset, which is one of the largest datasets of diabetic patients in the country, using open source libraries and we plan to create a centralized, robust dataset with inputs from tertiary centers around the world. The risks and mitigation that we talked about remain the same as before, where low resolution images are going to be modified with the help of the physical pinhole, and the AI model inaccuracies are going to be mitigated with the help of validation on a huge amount of data. Now, coming to the compromise that we have seen in certain parameters when we replace the parts of the device with cheaper alternatives. Firstly, the resolution is slightly decreased. The axial resolution, which is responsible for depth perception, may also be slightly affected. The field of view will be slightly smaller. The imaging speed will be slightly slower. However, a huge advantage that our device has is that it's going to be having a lot of enhanced portability, making it useful in resource poor settings. In addition, our diagnostic sensitivity will be slightly reduced, but the cost reduction is much greater, and it's still useful to be still useful as a screening tool. Coming to the clinical feasibility, this was the workflow that we'd already described earlier. And we know that the cost of the device is going to be highly reduced. Since the device cost is reduced by approximately 90%, the price of the individual test we envision can be brought to under 400 rupees per test, which can further be subsidized. This is an overall cost analysis where each of our components has been detailed, and our net cost comes out to approximately 4 lakh rupees per device, which is a cost reduction of approximately 95% with an accuracy reduction of just 10 to 15%, meaning that its use as a screening tool is not affected in any way. This was the market analysis that we have envisioned, where our initial aim is to be put into the 2,632 serviceable centers, which includes the community health centers, sub-district hospitals, and medical colleges. Eventually, we hope to partner with the government and make this device the standard of care, where we would start by rolling it out into the rest of the 8775 centers, followed by all primary healthcare centers and sub-centers in the country. These are some of the references that we've utilized. Thank you so much for listening. We hope you see the potential in this product the way we do. Thank you.
And any additional information about the technical design has been uploaded as well. Thank you.